Hey everybody, these are your notes on flat mirrors. The first thing I would like to do is just let you know, you got to record these in your notebook. Everything I write down, you should be writing down as well. You can pause the video if you'd like at any point, just to write stuff down if I move it too fast a pace. Alright, so first thing I'd like you to look at is not necessarily a mirror per se, but just look at the picture, and you've seen pictures like these before. There are mirror surfaces that are natural. You could probably think of many more than just this pond here, but there's a reason why some surfaces are reflective, some are all partially reflective too, and why some just simply don't seem to reflect light in this nice mirror-like way. This surface, because the water is so still, is called a specular surface. Specular basically means a smooth surface, and it's reflective. Alright, so draw the diagram below. It shows how light reflects off a specular surface. As you can see, the important thing in the diagram is you have this flat surface that is smooth. So that would be a mirror is an example of a specular surface. Another example would be a pond, like you just saw. You think of another example and add your own. So light that hits a specular surface, it all reflects in the same way. The angle it comes in at is the angle it leaves at, and that's why you can see a mirror image of objects from it. The other kind of surface is called a diffuse surface, and the diagram right there is below. Diffuse is a rough surface, and it's called diffuse because when the blue rays come in and hit the surface, this rough surface just scatters them all over the place, and there's no pattern to how they reflect. You can still see some of the rays, but they're kind of random, and they don't reflect in this ordered pattern, so it doesn't make a nice mirror image in a diffuse surface. So, no mirror image. Can you think of an example of a diffuse surface? Well, the pond or mirror certainly wouldn't be one, but anything else that isn't reflective is basically diffuse. It's too rough. My hand is a good example of a diffuse surface. It's not a mirror, so basically it is too rough to be reflective. It is diffuse. It diffuses the light rays that hit it all over the place, and it's not nice and reflective. Another thing you looked at in your investigation were distances and heights of images. You looked at DI, DO, HI, and HO, sometimes called Dido and Hi-Ho. Alright, so first thing we'd like to talk about is just, if you look at the image here, there's two sides to the mirror. There's a real side, where the person is really located, and our eye creates a virtual side to the mirror. And it perceives a space back there that doesn't really exist. That's what we call virtual, the space our eye perceives to exist behind the mirror. And there are two relationships with distance and height that relate to the real and virtual side of the image. So if we look on this diagram right here, we could label DO is the distance of the object. It's on the real side of the mirror. So where would DI be? The distance of the image doesn't really exist, but in our mind's eye it does, on the virtual side of the mirror. And what's the relationship between DI and DO? Well, if you went and measured DO and DI in your own drawing, you should get them to be equal. So, draw this, and I'm going to say DO here is about, you could take your own ruler and do this, but DO here I'm going to say is about 2 centimeters, and here it's also about 2 centimeters is what DI is. So we say DI equals DO for a flat mirror. Then we have HO and HI. The height of the object is HO, and the height of the image is HI. The image doesn't really have a height, but our eye perceives it to have a height. It's all created by our mind. So, define HO and HI, height of object and height of image. And what do we know? Our eye perceives the image of ourselves to be the same height as we are. And this works for any object. HI equals HO. What would happen if he took a step back? How would the distance of his image change? Well, if he stepped back to 3 centimeters from the mirror, his distance would also seem to step back to 3 centimeters behind the mirror, because the image distance always equals the object distance. If he crouched down and got shorter, so would his image seem to be shorter, because the image's height always equals the object's height. The last thing you discovered in your investigation had to do with angles at the height that light hits a mirror surface at. What you discover with angles is called the law of reflection. The law of reflection states that theta, that means an angle, theta I equals theta R. Theta I is the angle of incidence, and theta R is the angle of reflection. So I stands for incidence and R stands for reflection. So what is the angle of incidence and angle of reflection when light hits off a mirror? Well, the first thing we need to do, draw this diagram down here like I have set up. I have light coming into a mirror and leaving the mirror. This is the mirror's surface right down there. So label that. And perpendicular, or 90 degrees to the mirror's surface, we draw what's called a normal line. A normal line just means it's perpendicular. The word normal is just another word for perpendicular. And it's perpendicular, or 90 degrees to the mirror's surface. So we can see we have two rays here. And where it hits, we draw our normal line. The first ray, the incoming ray, is called the incident ray. Incident is basically another word for incoming. And the reflected ray is the ray that leaves the mirror. So where is our angle of incidence measured between? Well, our angle of incidence is always between the incident ray and the normal line. That's our angle of incidence right there. Not between the incident ray and the mirror. This is not our angle of incidence. This is our angle of incidence between the incident ray and the normal line. So our angle of reflection is also between just the reflected ray and the normal line. And whenever light hits a mirror, it simply acts like a pool ball. The angle it comes in at, the angle of incidence, let's call this 33 degrees. I don't know that it's that much, but if it is 33 degrees between the incident ray and the normal line, then our angle of reflection is also 33 degrees. Those two angles are always equal. Thanks, guys.